Hello, I'm Islam and welcome back to Mathematics 216. We have had our introduction already. Now it's time for us to start learning. And as we promised, we are going to start from the very beginning. It's a very good place to start, and we are going to start by revisiting our old friend matrices. Now I know a lot of you are already familiar with a matrix, but we are going to try to look at it from a different perspective, from a fresh perspective. We are going to try to see if we can learn something new. And for those who are kind of rusty on this subject, it's a very good chance for you to brush up those skills. Okay, so let's begin. Well, what are matrices? A matrix is a rectangular block of numbers. They will be enclosed in brackets, so it is basically as simple as that. You have a few numbers in a rectangular array, and there are two brackets enclosing it from either side. Now, why are these little block of numbers so important? Because these little blocks can store a lot of information very structurally and very efficiently in a compact way. For example, when you look at this picture, you are watching a graphical representation of data. But in your computer, how do you think this data is stored? If you zoom into it, this picture is going to look something like this, very pixelated. And in a grayscale picture, in a black and white picture, every pixel can have a value from 0 to 255. So we can just store every value of every pixel in a rectangular matrix. So this is actually how the pictures are stored in your computer. Now this is one way to store data. Let's look at another example that deals with data in a different way. So let's say Harry, Ron and Hermione live in the same street. So we have three houses. In the last week, Hermione didn't call Ron because there happens to be some fight going on over there. Ron tried to apologize once, so he made one phone call to Hermione. Harry is trying to resolve the issue, so he called Hermione 2 times. Hermione called back once. Harry called Ron twice, and Ron called back 3 times. So that's a lot of information, right? And it took us a lot of words to write them. But we could express the same amount of information using only a 3x3 matrix. That means only 9 numbers. So Harry did not call himself. He called Ron 2 times. So we have a 2 here. He also called Hermione 2 times. There is a 2 here. Ron called Harry thrice, did not call himself, called Hermione once. Hermione called Harry once, did not call Ron, did not call herself either. So, see, we can store who called whom, how many times with just 3 numbers. And for those who have already taken the data structure or 221 algorithm course, you already know that this is how we store a graph in a computer. This is called the adjacency matrix. And also, that's not all. This data, we can operate on this data using various matrix operations. But before we look at that, let's just revise the operations for a minute. So first of all, we have matrix addition. This is very straightforward. We have a matrix, we have another matrix. Now we want to add those two matrices. What we do, we add the individual elements. So we add 1 with 0 and get 1 plus 0, that is 1 here. And similarly, if we fill up the entire matrix, we'll have something like this. So we have 2 here, 1 here, so we have 2 plus 1 here. So this is obvious that for the addition to take place, the matrices have to have the same dimension. This is a 3x4 matrix, 3 rows, 4 columns. This is a 3x4 matrix. The result is a 3x4 matrix. If we had a 3x4 matrix and if this were a 5x5 matrix, we couldn't have done the addition. Similarly, subtraction is basically the same thing. Just instead of adding the numbers, we are subtracting the individual elements. And again, obviously, we have the same dimension here. If the dimension is not correct, we cannot do matrix operations. Now let's move forward to matrix row operations. There are 3 types of elementary row operations. First of all, rows can be interchanged. So if we interchange the first and second row here, we have got a new matrix. This is the interchanging of rows. Second operation, we can multiply a row with any scalar. What that means is, for example, in here, if we multiply the first row with a value of 2, we just multiply every element of that row with 2. The third operation is adding. Adding and subtraction is basically the same thing. Think of subtracting as adding a negative number, right? So we can add any multiple of any 2 rows. So if we multiply the first row with -1, we get -1 here, -4 here, and -2 here. And if we add that with the second row, we get a different matrix. So this is the third type of elementary row operations. You are going to see how and why we use these row operations in a matrix, and you are going to see that very soon in this very course. But for now, we are just brushing up our previous knowledge, so let's move on to matrix multiplication. Matrix multiplication is probably the most significant operation you are going to see about a matrix. Now, how do we multiply a matrix? We have a matrix here, we have another matrix here. We want to multiply it, but in this case we can't because the dimensions aren't right. Now this is a 3x4 matrix, this is also a 3x4 matrix, but for multiplication the rule is a little different. So the number of columns in the first matrix has to match the number of rows in the second matrix. So m into n matrix has to be multiplied with something that starts with n into k, and then we will get a matrix that is m into k in dimension. Now we have 4 columns here, but we have only 3 rows. So we either have to add one more row here or eliminate one more column. So let's just get rid of this column. Now we have the compatible dimension 3x3 with 3x4. If we multiply them, we get 3 into 4. So how do we multiply it? Well, for the first row, first column position, we take the first row of the first matrix and first column of the second matrix. We multiply each individual element, so 1 with 0, 2 with 0, 4 with 3, and then we sum them up. So we have 1 into 0 plus 2 into 0 plus 4 into 3. For the second row, first column position, we take the second row and the first column, do the same thing. Multiply individual elements, add them up. For the first row, second column position, take the first row, second column, multiply each element, add them up. Fill it up, the entire matrix, and you have multiplication at hand. Now, if we look at the dimension here, you can say that multiplying this matrix with this matrix is not the same as multiplying this with this. So A into B matrix, both are matrices here. A is a matrix, B is a matrix. This is not the same as B into A. A into B will almost every time give a different result than B into A. Now this is one way to look at matrix multiplication. In high school, in college, this is how we multiply two matrices. But there is a better, or at least a more interesting way, and we are going to learn about that, but not now. Unfortunately, you are not ready. We need to learn more stuff to understand that. Anyway, so let's move on. Now, a while ago, I did say that if we have a matrix, we can operate on that data. And then we looked at some of the operations. Now let's see how we can operate on this data. This is the data from those 3 houses in the last week. Let's say this is the data from those 3 houses in the week before. Now if we add them, what we get here is the total number of phone calls, so the data of the 2 weeks combined. So we can say that Harry called Ron 5 times in 2 weeks. If we subtract them, what we get is a difference. So we can say that Harry called Ron 1 times less in this week than the week before, and Ron called Harry 1 times more in this week than the week before. So see, addition and subtraction gives us new information from 2 matrices. Well, these are pretty silly examples, but I hope you are getting the picture that how matrix operation can be useful in a bunch of data. So let's see some other way we can use a matrix. This is probably the thing that you are gonna see the most in this course, because these are linear equations and this is the linear algebra course. You're gonna see this a lot. So let's look at it. We have a bunch of equations. Why are these linear? Because there is no power other than 1. X has a power of 1, Y has a power of 1, Z has a power of 1. So we don't have any power higher than 1. That's why they are called linear. Not important right now. We have 3 equations. These 3 equations, this whole system can be stored in a matrix. So let's look at this matrix. The first column here, it stores the coefficients of the x variable. So we have 2 from the first equation, 1 from the second equation, 0 from the third equation. Similarly, for the y coefficients, we have the second column 3, minus 2 and 1. For z, we have the third column 4, 2 and 1. Now, if we multiply this with this matrix, this is a 3 by 1 matrix, what do we get? We get 2 into x plus 3 into y plus 4 into z in this position, which is basically the first equation. So we have a 0 here. Similarly, 1 into x minus 2 into y and 2 into z. We have the second equation, which is equals to 0. So we have 0 here, and similarly we have 0 here as well. So this is a way to represent linear equations using matrix. A big portion of our course this semester is going to be dealing with this type of systems using this type of expressions. We are not going to go into that detail right now, but be assured you're gonna see these equations very soon. Anyway, let's look at another very interesting thing about a matrix. A matrix can also transform things. Let's see, we have a vector here. You can call it a vector, call it an arrow, doesn't matter. We are gonna talk about vectors in the next video more extensively. For now, we have a coordinate position that is 3 by 4. 3 in the x direction, 4 in the y direction. Let's multiply this with a 2 by 2 matrix. So this is a 2 by 2 matrix, this is a 2 into 1 matrix, so the multiplication is possible, and we're gonna get a 2 into 1 matrix, that is -4, 3. This is this vector. Now look at these two vectors. They have the same length, they just rotated 90 degrees. Now this can obviously be a coincidence, so let's try it one more time. Take another vector, multiply it with the same matrix, we get another vector here, and the same thing happened. This has the same length, just rotated 90 degrees. So what's happening here? Well, this is actually called a rotational matrix. You multiply it with any two-dimensional vector and the vector is going to rotate 90 degrees. There are other types of matrices that can rotate, that can scale or skew. All of these combinedly are called linear transformations. And as soon as we are done with these recap videos, we are going to start learning about linear transformations. Now that's all interesting, but let's look at a real life scenario, how we can use matrices in various ways. So let's say we have a small village, there are 300 people living in here. One day the coronavirus attacks, which is sad but well the reality. Every day 20% of the healthy population gets infected, and every day 10% of the infected people, they get well. So what happens now? Well, after the first day, after 20% got infected, we got 240 healthy people and 60 infected people. Well, what happens in the next day? Or what happens in the long run after a few months? Well, what happens in the next day is very straightforward. We have 240 persons, 20% of them is going to get affected, and 10% of the 60 persons that got affected last day are going to get well. So we have 198 persons on the next day who are still healthy, 102 persons who are sick. We can very quickly draft up a couple of equations that can express all of these. Of the 240 persons that were healthy, 80% remained healthy, and of the 60 persons that were sick, 10% became well. So this is our count of new healthy persons. Of the 240 persons that were healthy, 20% became sick. Of the 60 persons that were sick, 90% of them remained sick. So this is our new count of sick people. Now, this is a couple of linear equations, right? We saw a little while ago that we can express this using a matrix. So this is how we do it. So this is our matrix. This column is the coefficients of the healthy persons. So 80% remains healthy, 20% become sick. This column is the coefficients of infected people. 10% becomes healthy, 90% remains infected. So this is our equation. Pretty cool, huh? So we can use this equation anytime to find out what is going to be the counts of healthy and infected people on the next day. Now let's come to the question of what happens in the long run. Now notice here we are combining all the things that we just saw in this lecture together. Now we saw that a matrix multiplication changes a vector, right? So let's assume that every unit here corresponds to 50 persons. So we had a population of 300 healthy people. So this is the axis of healthy persons, this is the axis of sick persons. So if we multiply it with this matrix, we get 240 and 60. So this is our new vector. This matrix has transformed this vector into this vector. We have 240 healthy persons and 60 sick persons. If we multiply it one more time, as we saw in a minute ago, we will get 192 and 102. Similarly, if we had started with all sick people, we'd get this. Multiply it with the matrix, the vector would transform into somewhere there. 30 persons would become healthy and 270 of them would remain sick. So as you can see, these vectors are converging somewhere, and this is going to be that vector. When you have 100 healthy people and 200 sick people, that's going to be the equilibrium. Because if we do the calculation here, 80% of 100 plus 10% of 200 equals to 100. 20% of 100 and 90% of 200 equals to 200. So the vector doesn't change anymore. This vector is called the eigenvector. This is going to come up too in this course. Very important topic, but much later. Anyway, I hope we could do a decent overview on matrices, brushed up our existing knowledge, tried to look at matrices from a different perspective, and that's gonna be it for today. On the next lecture, we are going to talk about vectors. So thank you everyone, and I will see you again.